Welcome to 7th lecture of video course on tribology. Today's topic is adhesive wear. In last lecture, we understood wear mechanism related to abrasion, scratching, or sometimes we call it scoring. This adhesive wear is more related to the adhesion friction. We say that when two materials have affinity for each other, they make some bond. It may be molecular bond, which is very strong, difficult to shear. And if that happens, there will be enormous wear. If we can reduce the strength of that molecular bond, then wear rate can be reduced. And generally, understanding this topic helps us how to reduce shear strength of that bond. Let us take a common example which is mostly quoted in books. We say that adhesive wear mostly occurs in metals, slightly lesser in ceramics, and in polymers. If load is within limit, within transition limit, then this kind of wear will not occur. But if the transition is above transition limit, whether some plastic deformation is possible, then that kind of wear occurs. So, here in this diagram, three stages are shown. One is a steel pin, many times we can call as a steel rider, an indium block or indium disc. If we press steel pin with some force, some normal force, maybe say W, it will try to indent in indium, something which is shown in figure B. Now, if we retract it back, it will come up with some sort of deposition on a steel surface and some depth, some removal of material from the indium block. The indium has a affinity towards the steel. It makes a bond, it makes a molecular bond with the steel, and then indium strength is slightly lower, bulk strength, obviously the cohesion force is lower. So, it leaves a fragment, it transfers the fragment to the steel surface, and same thing happened with the brass also. If we try same thing with the brass pin, indent in indium, it will give some sort of transformation of indium on the brass material. Let us take another situation. Say we know all the surfaces or the molecular level are rough. They have some amplitude about the mean value, and if load is applied, normal load is applied, there is a possibility of junction formation, which was explained in detail in a friction lecture. This red spot is shown some area of contact, and we know this area of contact is much lesser than apparent area. Naturally, almost every aspirative will be undergoing plastic deformation and to some extent limit up to the elastic limit if it can easily bend. Now, if we provide some sort of a lubricant layer, or there is no chemical affinity of this metal 1 and metal 2, then there is a possibility of easy shearing of that surface, or breaking the bonds will be easier. There will not be much wear. Of course, there will be wear, some fragment will be still getting torn away from the surface. So, there will be wear, what we call that as a mild wear, mild adhesive wear. Take an example of severe wear. See aspirative coming into contact, undergoing the plastic zone, and what we call this as a micro welt. Now, if we push it with a tangential force, there is a possibility of junction growth and plucking out our material, a blue color material on this. This red color is shown because generally the microstructure will be changed. It will not be as it is a blue color. this surface is slightly hardened, obviously the affinity of this red portion is higher, chemical affinity towards the green metal is higher. So, metal will be getting transferred and this is a bigger chunk. We can say it is a severe wear. So, and based on this slide I can say adhesive wears can be classified in mild wear and severe wear. We will be studying this slightly later after some time on when we come to the 7th slide of this course or this lecture. But let us quantify this wear mechanism or how the adhesive wear occurs. Whenever we want to quantify wear volume or rate of wear, always we start with the real area of contact, because the wear generally occurs at the area of contact. If there is no area of contact, there will not be any wear. If the two surfaces are completely separated by the lubricant layer, then there will not be any wear. But if they are intimated, they are superimposed or there is some common area, one metal is penetrated in another material and there is some sort of weld junction which need to be plugged out or need to be removed or need to be sheared, then there is a possibility of wear. So, to find out that real area of contact, we can use this equation, the simple equation. It says A is equal to W by H. Here W is a normal load, which Amundsen defined that it is always a normal load which matters. It is not the dead weight, it is a normal load. It is divided by the hardness H, which is the hardness of softer material, whichever the weaker material. However, in this basic assumption is that there is a plastic deformation. That is why the H has been used. H is a flow stress, allows material to resist up to this limit, and if you increase pressure, normal pressure more than that, then it will allow surface to penetrate easily. So, that is why the H is a flow stress, and then this area A is equal to W by H is valid only for plastic weld or weld made after the plastic deformation. But we know very well there will be always some asperities, very high height or low height. Not all asperities will undergo plastic deformation. There will be contact at the elastic limits also, and separating two surfaces at the elastic limit will not be much problem. Effectively, area of contact will reduce. If there is a plastic deformation, naturally more area will be in the contact. There is a deformation, some flattening of surface, more area of contact will be there. So, when we talk about the elastoplastic junction, when there is a elastic deformation as well as a plastic deformation, we can say area can be modified using parameter n, where n is lesser than 1, but greater than 66% or greater than 2 by 3. This is the modified area of contact has been established by a number of researchers. But what is the difficulty? Difficulty is that how to find out this n, which is very tedious, and it will vary from one component to another component, will vary from one situation to another situation. Sometimes we have oxide layers, sometimes we do not have oxide layers, sometimes we have water presence, sometimes we do not have water presence. So, every time if I do some experiment, I will be finding different relation for n. N is uncertain parameter, depends on number of variables. We can think about other option also. If I go with this kind of theory, then what is the possibilities? There is a weaker junction or a stronger junction. If there is a more and more plastic deformation, junction will be stronger at one point, the more area of contact, but in addition there is a shear strength of the junction. There is a possibility more area of contact, but lesser shear strength of the interface. In that case, friction force will be lesser and area of contact even though larger, but wear rate will be lesser. However, if shear strength of the junction is higher, then wear rate will be higher. So, whenever we talk about the modeling wear rate, we need to account area of contact as well as what will be the shear strength. See, there is a possibility of weaker junction, there is a possibility of a stronger junction. The shearing occurs at the interface itself. The shearing occurs at interface, it is a mild wear, and if shearing occurs at the little distance within the one of the metal, and one of the metal is a softer metal in this case, then it will be severe wear. More and more material will be plugged out from the surface. So, we need to account area, we need to account strength. An interesting thing is that it is very difficult to find out the shear strength of the interface, particularly when the few asperities are plastically deformed and few are only elastically deformed. We know very well to shear plastic junction we require more force. To shear elastic junction we do not require much force. That means, we need to count at every asperity what will be the shear strength, which is very tedious job, is highly statistical. Naturally, we need to find out some good relation which can avoid these many complexities or all these complexities. This may be good for the research work when we want to concentrate only one machine component and try to do analysis of that machine component. But when we talk about the generalization, when we talk about the theory, when we talk about the common equation, these equations will be, or this kind of a variable will give more and more difficulties. To demonstrate what I explained in the slide, we are taking example of steel versus tin, steel versus lead. When steel and tin are in pair, the steel is subjected to some normal load. We again the surface 1, surface 2, and here there is a interface shear strength also, as here has been represented as an interface shear strength SI. S1 may be strength or shear strength of steel, and S2 as a shear strength of tin. What we are saying in this case, that SI is the lesser than S1, SI is the lesser than S2. That means, interface shear strength is lower compared to steel, is a lower compared to tin, or is the lowest among 3. So, in this case we can assume there will be mild wear. Even in absence of lubricant, there will not be severe wear. Interface is low shear strength. Take another example of steel versus lead. We know that we have heard a number of times the lead been deposited on a steel surface, make a thin layer on the steel surface and used as a lubricant layer on that. This is because a good adhesion between the lead and steel. However, when the one component is made of steel and other component is made of the lead, and they come in a contact under load condition, subjected to sliding condition as well, then there is a possibility of plugging out lead material, more wear, severe wear. Reason is, here the interface shear strength is lesser than steel, but interface shear strength is greater than lead. That means, interface which is made will not be torn away, will not be wear out in normal conditions, but a lead will be plugged out from the surface, and that is going to make a surface rougher surface, or steel surface will be rougher. Adhesion will lead to the abrasion wear, and that will cause a catastrophic wear, or it causes as a severe wear. There is another possibility. When we say that copper and steel are coming into contact, they have a good adhesion, they make a good strength at the bond. Interestingly, in this case interface shear strength is a greater than steel, as well as interface shear strength depends is a greater than shear strength of copper. So, we are looser at both the ends. Shear strength is a higher, and it will be unpredictable for us whether steel surface is going to lose material or copper surface is going to lose material. It may be randomized. Wherever the more asperities of steel and a lesser high magnitude asperities at the steel, more cantilever length, naturally asperity will be plugged out from the steel surface. If the asperity height is very high in a copper, that surface will be worn out. So, depends on surface toughness, depends on the shear strength of individual material, and depends on the how the load is applied, whether one component is applied in some normal side also. So, the resultant force is some at the angle at the interface, it is not along the interface. Then material wear will be high. That is why we say that we do not use a copper and a steel as such without treatment. If you are treating, you are increasing hardness, you are trying to reduce the adhesion between the steel and copper, then it can be used, otherwise it cannot be used as a tribo pair, as a sliding pair. Reason being, there is a high wear rate between steel and copper. When they make interface, interface is much stronger than copper strength, and interface strength is a higher compared to the steel strength. So, that is why we try to avoid this kind of pair, or if otherwise we need to provide some lubricant, and we know very well whenever there is a lubricant, shear strength of lubricant will be much lower than interface shear strength, or we say that parent material shear strength and interface which is made with a lubricant will be having lesser shear strength, and it will be easily tear out, and it will not cause much wear. It is interesting to see how adhesive wear progress. It will not be spontaneous. There are some stages involved in adhesive wear. We can prevent at any stage. See, the first is the deformation of contacting asperities. Asperities come into contact with material and deform the surface. It's something like this. I am assuming this is a one surface, rough surface. It is coming under load to the other surface, and the other surface has a contamination layer, adsorbed layer, oxide layer, work hardening layer, and metal surface, which was earlier shown in a friction lecture. But when this rough surface comes into contact, it will start deforming the contacting asperities or surface, which is opposite to this main surface. Because of that, there will be some sort of penetration and removal of protective oxide layer. If the surface is stronger, penetration is there, there will be fracture of the oxide layer, it will be fragmented, and once it is fragmented, it can be easily removed. So, if there is a removal of oxide layer, then only the nascent surface will be there, or the virgin surface will be there, pure metal will be there, and we know very well pure metal will cause more adhesion compared to the oxide adhesion, which will create some more problem. So, the formation will start once we remove the oxide layer. If there is a fracture, the removal of the oxide layer, there is a possibility of adhesive junctions, which we have studied also in the friction chapter. However, there is a possibility of work hardening of the metal, which may increase strength, but if that layer is also removed, then there is a more chance of wear. We can project this something like this. We say that most of the layers have been removed. Now, there is only work hardened layer is remaining, and if there is a possibility of fracture of this layer or change in the properties, which may bring some more brittleness and which removes the piece as it is from the surface. After removal, there will be some loose pieces, and there is a possibility of more and more wear. We can demonstrate same with one mechanism, a gradual mechanism, something like this. We say that let us take one surface coming into contact with the other surface, and this surface has a relative velocity. This surface is subjected to load. We know at the micro scales, every surface is rough surface, and contact will occur on the asperities. For sake of simplicity, we are showing only one asperating, so that we can understand the phenomena. Otherwise, every surface will be having enormous number of asperities, but for time being we are assuming there are some n number of asperities, and every asperity will behave more or less similar manner. Even though we know that is an approximation, that is not a very good approximation, but for understanding the mechanism, understanding the physics, this helps. So, when the surface is pressed and is under load, there is a chemical affinity of a material 1 towards a chemical affinity of material 2, then there is a possibility of penetration because of surface roughness as well as formation of junction. And if it is a mood, there is a possibility of very micron level size particle is plugged from one material to other material. That is why we are writing as a junction failure and plucking of one material to other material is something like this. When it moves, this material has a one small additional asperity, and this additional asperity is the material asperity of the material 2. It is not its own asperity. The material has been transferred from surface 2 to the surface 1. That is a transfer, that is the addition. Once it happens under one asperity, similar behavior will occur at a number of places. So, we can say there is a possibility of number of asperities or additional asperities or additional protrusions on the material 1, but there is also possibility if the material have a relatively same hardness or same chemical affinity, that other material also can get some material from the surface 1. So, just for completeness we are showing that both the surfaces have some protrusions or some additional asperities which were plugged from the other surface. If it continues, surface will keep getting irregular, surface area contact will reduce, stress on the surface will increase, and there is a possibility of junction growths. Initially, there was only one choda asperity or smaller size asperities, and then it is getting more and more on that the area is continuously increasing, not only area surface area, but the height is also increasing. So, what we say that increase in the length of cantilever or unsupported surface. This is unsupported surface is continuously increasing. When continuous increase unsupported surface, naturally there is a possibility of failure of that surface. This is what this is a maximum size, asperity has grown up too much, and now even the small force can tear away this complete material, can plug out or can remove from the surface 1 itself as a loose particle. That happens like that when it comes in the loose particle, and if there is a force on a surface 1 which is getting transferred on the surface 2, then this loose particle will get flattened, it will be under compression, and again the process will start. This is creating a third particle or a third component in between, which will have a different microstructure, will have a different hardness, they will have a different chemical affinity towards a material 1 and material 2. So, this process continues. We start from adhesion, there is a possibility of particle generation and bigger particle first, and then it will be disintegrated in number of smaller particles. So, adhesion force or adhesive wear at the start, and it may turn out to be abrasive wear at a later stage if the hardness of this particle is much larger than parent materials. It will cause abrasion wear. So, one wear mechanism is leading to other wear mechanism, and that is why we say that most of the failures are happening because of abrasion. Abrasion percentage is much higher than adhesion percentage, and adhesive wear comes on the second number in the list. Highest percentage failure is because of the abrasion, and second number is adhesion. However, if we see in a deeper side, most of the time is the adhesion which is initiating the wear, but what is the result which is identified the final, that is caused by the abrasion. So, we cannot say in an absolute sense that abrasion is much more dominant compared to adhesion, or more frequently occur in compared to adhesion. There is a possibility adhesion starts and finalized or come finally to the abrasion mode. So, there is a possibility 50%, if the overall percentage between adhesion and abrasion is 70%, I can assume that 35% goes to abrasion and 35% goes to adhesion. A micro level mechanisms are generally starting with adhesion, tearing the junction, generating the loose particles which lead to the abrasion. In this case, we can finalize, we can conclude this slide. We say that wear may be defined as a gradual removal of the discrete particles. Not necessarily the big particle need to be plugged out. There is a possibility of small discrete particle size coming out of the surface as a result of mechanical action. Why we are saying the mechanical action? This whole process is a mechanical, it is not a chemical. One wear mechanism we know, the corrosion wear, which is basically a chemical nature, but again the wear occurs, the loss of the material will occur because of the mechanical action. Generation of a layer which is a loose or having a lesser strength, which can be easily fragmented, is possible through the chemical action, but removal of that layer from the surface is only possible through the mechanical action. It will not be like corrosive layer which come its own. It need to be tear away, it need to have some mechanical work on that. That is why we say that wear may be defined as a gradual removal of the discrete material, discrete particles from the surface as a result of mechanical action. So, mechanical action is being emphasized on that. For every wear, mechanical action need to be there. That is why we need to reduce as far as possible to avoid the wear or to minimize the wear. To quantify, we started with the quantification of the wear and we came to the first area of contact and then shear strength. It was realized that it is very difficult to quantify as it is from the physics point of view. So, people started working on that and they did a number of experiments. We know the Bowden and Tabor gave the theory of adhesion, junction growth and friction due to adhesion, but later it was modified or converted by Archard after doing number of experiments on a similar mechanism. What he came to conclusion is that wear volume is generally proportional to sliding distance, which is obvious. If we the contact surface traverse more and more, naturally wear particle removal of wear particle will be more and more. However, exactly it will be proportional or not, we do not know, but it was concluded by Archard that generally it is proportional to the sliding distance. More and more sliding distance, more and more wear, and that in same proportion. However, there is some discussion on that. We say that quite possible initially there is more wear, but later it will not be having more wear. So, it should not be said that it is always proportional to L. There is a possibility of changing one wear rate from one condition to other condition, and we know that the wear is a dynamic process. Changing one condition from one condition to other condition is always there. So, from understanding point of view, we can say it is it depends on the distance of the travel, and if we are able to do some experiments, we can still believe that the wear volume is proportional to L, but there will be some constant that may give us some sort of probability of removal of material. So, we need a constant along with this. Second conclusion which Archard gave after doing experiment is that wear volume is proportional to the load, which is also there because the friction force was initially treated as a proportional to the load. In that case, similar way we are assuming the wear volume which is removed from the surface is proportional to the load, but there is a limit if it is subject to the plastic deformation. If it is not subject to the plastic deformation, then it will not be proportional to the load, it will be slightly lesser than that, or effect of the load will not be that high, there is a possibility of reduction in that. So, if we use this law, then we need some relation or some constant along with that, which can modify this depends on the area of contact. For time being, we can assume this is proportional to W. And finally, he gave third interpretation. He said the wear volume is inversely proportional to hardness of softer material, which also comes from the friction side. Higher and higher hardness, lesser and lesser will be adhesion, and if there is a lesser and lesser adhesion, there is a lesser and lesser wear volume. From that angle also we agree, but again exactly inversely proportional we cannot conclude on that. There is a dependence. We say the wear volume depends on L, wear volume depends on W, wear volume depends on the hardness H. But whether it is 100% proportionality is there or not, is it directly proportional or not, there is a possibility of some power loss, some factor N. That is why finally the Wear equation which came from Archard is given as a V is equal to K1 W L divided by 3 H. Now, here hardness of the softer material, L is the traverse distance and W is a normal load, but there is a constant K1. Quite possible constant K1 is also accounting the factor W, proportional, whether directly proportional should be there or not, and also accounting the length traversed, and is also defining whether the relation or volume is directly inversely proportional to H or not. This Wear constant can be manipulated. We can do a number of experiments. We assume this is a curve fit equation, find the W, measure L and measure H. Based on that, whatever the Wear volume comes, we can appropriately find K1. If we do the 30 experiment or 40 experiments, the statistical variation between K1 for the K1 can be measured easily or can be estimated easily with some standard deviation. However, it has been interpreted also this kind of Wear equation is valid only for the linear profile. Wherever there is a transition due to change in the load, if there is a wear rate suddenly increases, this equation cannot be utilized. Just for the completeness, we are showing this curve where the axis of wear rate and the load, and we say that as a load is increasing, there is a possibility of increase in the wear rate. So, there is a proportionality which is shown in this case, and number of data, and this data are experimental data, and there is a curve fit equation in that. We can find there is some variation in that, some statistical variation is there, but if the variation is neglected, we assume the mean value. We can say from this experiment, yeah, for stainless steel this is followed. Similarly, for the brass material, yeah, that is also followed, this proportionality is followed. However, for the steel or stainless steel, beyond certain load, we are able to find out there is a sudden change in wear rate. This sudden change in wear rate generally occurs because of the deformation or removal of the oxide layer. Assume that initially the stainless steel has some sort of contamination layer, and after certain load, when the certain load is applied, that layer is deformed, fractured and removed from the surface. Then there is a jump in wear rate. You can see the wear rate of the stainless steel is crossing the brass material. In this case, after certain load, the stainless steel will show worse performance compared to the brass material. So, there is a possibility of transition load and need to be incorporated, or at least when we do number of experiments, we should figure out what is the transition load, and we should load the component below that load, or we apply a normal load or maximum load which we transferring from one surface to another surface, that need to be lesser than its transition limit. Here this equation shows that we are counting here only the plastic wear, or the plastic deformation and wear is causing after that. However, if we count elastic plastic domain together, then this equation should be modified. We say that instead of W by H directly, we should write W by H power n, and n is lesser than 1. However, there is a possibility or there is a difficulty to find out n. We know there is a one wear constant K1, and if we introduce this one, there will be two wear constants, and figuring out the two wear constants, we require many more experiments and manifold experiments to get the reliable results. So, in that view, when we are working only the one pair or two pairs, we can use this generalized equation. We use input W, L and H and figure out what will be the value of K1 after doing number of experiments and reliably believing on after that experiment. Now, how Archard has reached to this equation? He did a number of experiments and he tried to give some sort of mathematical justification also, assuming the asperities are spherical in nature, and under classic deformation they flatten it, something like this. There are two asperities. If I see the cross section of the asperity, there is a circular. However, when I see the deformed surface is a flat. So, the surface is getting flat after deformation, after plastic deformation, and when the two surfaces move related to each other, one aspirity is moving related to other. Initially, this is the angle of approach or start of sliding. When it crosses over, there is area of contact. Slowly area of contact reaches to maximum value, and after that again is reduced and comes to 0. And this happens for the number of asperities, and the number will be parallel asperities. So, there will be always some area of contact, and few asperities will be in contact and few asperities will not be in contact. There is some fraction of that. However, to come to the real relation, what Archard assumed initially that contact occurs only at the asperities. Without asperities, there is no contact. That is true, that is a valid assumption, and then he wrote that real area of contact can be given by finding the area of contact of individual asperities and summing up all those areas. That is also valid, the justification is proper. However, only the problem with this equation was the plastic deformation. He assumed there is a plastic deformation, and if we take that plastic deformation in account, we can say that one asperity will bear some delta load that can be given by some constant k 1. We are not 100% sure that there will be area of contact or complete area of contact, or what will be the area as such asperity in this case, whether A will be really A or not. So, that pi A square, and along with that there is a hardness, whether complete asperity is in contact or not, and this constant is given as a proportionality constant in this case. This is the area normal load which can be sustained or can be bared by the asperities. There is a possibility of wear of that asperities. So, that is given by delta volume, that is another constant k 2, and this is a half of the volume, the 2 pi a cube divided by 3. That is assuming the hemisphere half will be removed, or this area will be removed from the surface. So, this is a big assumption, a very we say that crude assumption. Whole asperity will be removed in one go itself. When the one surface is traveling on another surface, the whole asperity will be sheared away, which is a very crude assumption. However, that can be accounted because he has accounted k 2 as a factor. If we assume that k 2 is much smaller, then we can assume is only a fraction of the area is being removed. It is not 100% area. If the k 2 is equal to 1, then only the 100%. So, if I combine this, pi a square is here, pi a square is here, we can combine it, we find out what will be the load in terms of h and in terms of area, and when substitute it can get the relation V. In this case, the small v is a volume per unit length, and we are assuming the unit length of contact is 2 a. Maximum which is coming into contact area is a 2 a. So, that is accounted here wear per unit length. When we substitute from here pi a square in this equation, here it is V is given the volume per unit length, that means mm square, constant k 2 pi a square divided by 3. So, this pi a square is common, this pi square is common, and this both are summation. We do not have to count the number of asperities. It can be n, can be 2 n, can be n 3, 3 n, and n can be anything. So, is the easiest expression for us to remove pi a square, which is uncertain for us. So, substitute this value, we can finally get V as a k 1. Here k 1 itself is a ratio of k 1 by 2 k 2. So, that is another constant, W is there and H is here, and if you account real sliding distance, whether all asperities are coming to account and complete length, travel length is L, that can be multiplied with the W to find out overall volume, that is in mm cube or centimeter cube or meter cube, whichever unit you use. So, there is a W normal load, there is a L, there is a H, and there is a 3 is a factor which is directly coming from here. In many books, we generally find out the k 1 by 3 itself is a factor. So, they write a constant k where constant k as it is. They write where constant k into W into L divided by H. They do not count the 3 factor because that is a constant. We know that where 3 itself is a constant. So, one constant divided by other constant will remain constant. and that can be represented only with one constant. That is possible. So, Wear equation can be given, and this is the same equation what Archard gave, interpreted from his own experiments, and then gave a 3 law of adhesive wear. Is proportional to the sliding distance, is proportional to normal load, is inversely proportional to hardness. You increase sliding distance, wear rate will increase. You increase load, wear rate will increase. You increase hardness, wear rate will decrease. So, this is the same thing which Archard gave initially and proved mathematically also. However, the interesting thing is that we need to observe how K1 will change. This will help us how to reduce the wear rate. Let us take first example. When K1 is equal to 1, that wear constant is equal to 1. What is the meaning of that? Every junction involved in the friction process or friction adhesion process is going to produce a wear fragment. Whatever the junction is made, that is going to get sheared with some wear particle. And that is a slightly unrealistic. We know that even static case, we will not be applying that much load. Yeah, if there is a fatigue case, particle will sustain some cycles, and it will be wear out after some cycle, maybe 10 cycles, 20 cycles, 100 cycles, 1000 cycles. So, this is highly unrealistic, but from understanding point of view, yes, K1 is equal to 1 means all this junction are going to tear away, are going to generate wear particle. If there are 1000 junction at any time, so there will be 1000 particles generated in one go, and next time it again will increase accordingly. Now, if we reduce to 0.1, that is a 1/10 of earlier case, slightly there is a possibility of that. Say the 1/10 of friction junction produce a wear fragments, and that is the case with a gold surface. For the clean gold surface, they get attached, they make very strong bond, coefficient of friction is very high, and if you want to really tear it, somewhere it comes up between 0.1 to 1, but more or less is related to 0.1, 0.2, 0.3. There is a possibility of this. So, we say that wear rate is high. However, in when you treat copper, clean copper, wear rate is slightly lesser than which is 1/10 of gold itself. You say that for clean copper, this K1 will be in a range of 0.1 to 0.01. That means, using copper is better than using gold. We know the price of the gold is much higher than copper. So, it is always advisable, if you have a chance, better use a copper. If thermal conductivity is required or some other properties are required, use a copper in that case. And the conclusion from these two sentences is that a clean gold surface wear out about 10 times more rapidly than clean copper surfaces. We are using the word clean, we are assuming that there is no contamination layer on that. Surface is an essence, there is no additional material on that, it is a pure gold, no oxide formation, no lubricant layer, nothing on that, it is a pure gold and pure copper. However, this is more realistic when we say the K1 is equal to 10⁻⁷, and this is generally our aim, a designer aim over there. So, the 10⁻⁷ means the junctions responsible for friction, only 1/10 of the million produce, we say that if undergoing another 10 million cycles, then only one wear particle is produced. That is acceptable as we know the materials will be subjected to the loose particles after number of cycles. And when the components are new, initially there will be wear out because of the bedding in time, because of the asperities deformation, or when surface is initially rough, if there is no much compatibility between this, there is no conformity, initially wear rate will be high, but after that it will reach to steady state condition, there will be generation of loose particle, but after certain cycles, this is what indicated over here, generally after 10 million cycle, the one particle is generated and it can be lost from the surface, which is more realistic for us, and we can accept it right now. What we can conclude from this slide is that K1 is a dimensionless constant. It does not have any dimension, it does not have mm or mm cube, it is a dimensionless in this case. What we have, the way we have treated is a dimensional constant, and it can be given as a probability of removing a wear particle. we are using very strong word probability over here, but it appears that it shows the probability of the wear junction removal, or the breakage of the junction with the particle, or removing particle from the junctions, or taking out the particle, or plugging out the particle and making it the loose particle. So, there is a possibility, or we can say that we can use a word as a probability for K 1. It is a probability of removing of wear particle. Again, in this case, an overall expression, we assume only spherical asperities. We are not assume any other asperity, but there is a possibility of other form of the asperities, and then K 1 will be will be slightly higher than a spherical. There is a possibility, and then wear rate will be slightly higher. This we have expressed adhesion friction on friction due to adhesion process. We have a given relation for the wear rate due to adhesion. So, there is a possibility of some relation between that coefficient of friction and wear constant. Some studies show that there is a strong correlation, and some studies show there is a not much relation, they are not related at all. You say like gold or gold, the coefficient of friction is roughly 2.5 to 3, while wear constant is a 0.1 to 1. Now, if I reduce this coefficient of friction for some other surface, is a copper on copper is from 2.5 to 1.2, wear rate is decreasing by 10 times. Here we have reduced the coefficient of friction by 2 times, and wear rate is reduced by 10 times. Now, further 1.2 to 0.6, you reduce wear rate by 50%, and we are able to reduce also wear rate to some extent, but as this is given in a range, we cannot say what is the range. It may be from 1 to 10 times. Reduce the wear rate further from 0.6 to 0.3. Here we find a big jump, wear rate is reduced significantly, again the 10 times, from 0.01 to 0.001. So, this more or less it says that if you reduce a wear coefficient friction coefficient by 1/2, wear rate is coming by 1/10. That's the advantage. We say that if we are able to control the coefficient of friction, we are able to control wear constant also. So, here from 0.3 to 0.15, wear rate is reduced significantly here. You can say 2 into 10 raised to minus 5. Now, there is a problem. We are reducing wear rate by 50%, and this is reduced by 1/10, 150 times. So, 1/50th of this, and further increase in the coefficient of friction. Teflon on hard steel is 0.15, and stainless steel on hard steel is a 0.5. Even though wear coefficient is increased, but wear rate remains same. And these data show that there is no correlation between coefficient of friction and wear rate, while these data are indicating there is a correlation between the friction and wear constant. Same thing here. In this case, even though wear rate is coefficient of friction has increased from 0.5 to 0.6, but still there is a reduction in wear rate. They are going in opposite direction. We are not increasing the coefficient of friction, but we are increasing coefficient of friction, but we are reducing the wear rate. So, there are a number of other parameters which are playing a role in this. May quite possible environment plays a role when it has been done, or when experiments when performed. In totality or in a short, we say that there is no definite relation for the wear and wear constant, wear and friction, or is like wear constant and friction surface. However, Roy has given some relation. We say that sliding distance as wear volume per unit sliding distance can be represented in this relation. Here, directly proportional to W, inversely proportional to hardness has been accepted as it is as the Archard did. However, instead of wear constant 1, K 1, here it has been written Km square root of the 1 plus mu square, as a coefficient of friction, and there is a beta as a fraction, and this beta indicates what is the lubricant layer thickness, how much area has been occupied by lubricant layer. And how much area is the dry area. So, beta basically represent the dry area, no lubricant layer, it will be lesser than 1. In other words, 1 minus beta times area is covered with a lubricant. So, the shear strength will be negligible compared to shear strength of asperities or interface, solid interface. In addition, he introduced the 1 plus mu square, the coefficient of friction. As such, is we know the coefficient of friction may be 0.2, 0.3, 0.4. If I make it a square, it will turn out to be 1.16. It will not be very high value. It is not going to change much in magnitude. But problem in this equation is that we are introducing wear constant Km, we are introducing coefficient of friction, we are introducing the beta. So, there are 3 unknowns, and an Archard equation there was only one unknown. That is why the Archard equation is a more popular compared to the Rowe equation, even though Rowe say that is a modified Archard equation, but it does not gain much popularity. Reason behind that is that it has a 3 constants, and if these 3 constants cannot be given directly by theory, it will need to be experimentally measured, then complexities are going to increase. And we can say, if I have to do the same number of experiments, this equation will be preferred because there is only one wear constant. I require lesser number of experiments for that. However, the Rowe has supported that with the lubricant layer the things will change. This same equation can be the Archard equation also can be interpreted in similar manner. We say that if there is a more and more lubricant layer, K1 will keep on decreasing. So, there is not much problem for us. In my view, using Archard equation still is preferable compared to using modified adhesion wear theory equation or Rowe equation, because it has a more number of unknowns compared to this equation, which has a lesser number of unknowns. And wherever there is a lesser number of unknowns, and we know that this equation cannot be relied as it is, we need to do some experiment to find out the results. From that point of view, I can recommend using Archard equation compared to Rowe equation. There is another theory related to probability. So, because Archard express the K1 is as such the probability of how many junctions are going to tear away or going to give particles. So, and that relation is valid for the spherical asperities. Some modification have come in have been proposed by the researcher. He said that instead of using a spherical, we can use any rectangular or any other dimension where the thickness of the asperities can be given as by h and length of asperity can be given by L. Use this relation to quantify wear equation, instead of writing directly K1 as a constant, write K1 in this term. What is the probability of junction failure which produce a particle, and what is the thickness of asperity, and this can clearly indicate that the thickness is not very large, or maybe say the ratio is smaller, the wear constant will be lesser. We say that rougher the surface, wear constant will be larger. In this case, if h is a greater than L, the asperity height is much larger than is expansion of or the length of the asperity, naturally wear constant will increase. So, this is to some extent accepted, this kind of relation can be accepted as it is, but only the difficulty is in how to find out h, how to find out length, and how to find out the probability. Even though we know that if we do number of experiments, again h and L will keep coming in this. So, it can be used or can be interpreted as a qualitative manner, not in complete quantitative manner, because we require to find out h and L and a statistical distribution, and based on that find out what will be the wear rate. So, again my recommendation is we use this equation if you are thinking about a one set of condition, one operating condition, and you want to operate some machine components and want to test that, this is good option. Excuse me. Now, some interpretation based on experimental results, we can interpret something like this. We say that if I am choosing a metal 1 as material 1 as a metal and material 2 as a metal, wear constant will be greater than if I choose material 1 as a non-metal and material 2 as a metal. So, that is by and large will be valid. In other view or in other word, we choose non-metal and metal combination compared to choosing metal-metal combination from adhesion point of view. We are not talking of the fracture point of view, we are not talking about the strength point of view. Here is a simple adhesion point of view, because we know the metal has a more affinity towards a metal compared to metal and non-metal. Similarly, if I want to choose a metal and metal, I will prefer, instead of that, if I other requirements are satisfied, I will choose non-metal versus non-metal. That is going to give me lesser wear coefficient, and lesser wear coefficient means a longer life of the component. So, we can say and third recommendation, we can suggest third option is that if you are using metal A versus metal A, they are similar microstructure, I mean similar material, then naturally they will have more affinity, they will make a stronger bond compared to metal A and metal B, right. So, if I have options, we say that I will prefer always non-metal versus non-metal if all other constraints are satisfied. Next option, if I am not this is a constraint one way or another way, will be going for the non-metal and metal. If that is also constrained, we have to use only metal because of some other restriction, then I will prefer to choose metal A and metal B. They are two different metal, we will not choose the same material. However, if again there is a constraint, then we need to have some sort of hardness factor. We need to say that they are work hardened so much that they lose their adhesion property or affinity in this case, right. So, we say that finally, the degree of whether wear rate will be high or low depends on the compatibility of two metals, and this compatibility means that how they are able to oppose their adhesion bond junction. If they are able to make a weak bond at the interface, they are compatible with each other, there is no complete bonding or firm bonding, then that kind of metals can be used. Otherwise, we should not use that kind of material pair. With this, I am concluding my today's lecture. Thanks for your attention. We will continue adhesive wear in our next lecture. Thank you.